it's fantastic for me to be here. I'm really excited to be able to present to you. And let me share the screen here. And hopefully, is that working okay for you?
Looks perfect.
Great, excellent. So as you said, I'm going to be talking today about next generation collaboration technologies. And I don't know about all of you, but my workplace right now kind of looks like this. We basically get up in the morning and spend lots of time on Zoom with classes and teaching people, and then back to bed. So for some of you and myself, I've been feeling really tired by this. And it turns out that this Zoom fatigue is actually a thing. You can go online and look for it. And there's many articles published about why we get tired when we're doing conferencing all the time. And there's three main reasons. First of all, there's a number of physical factors. So we sit at the computer all the time. We're staring at a fixed screen. Oftentimes we work longer hours. There's also cognitive factors. You know, when you're looking at somebody on the screen, you lose some non-verbal cues you normally have face-to-face. You need to focus more intently. Sometimes people often will multitask. I was teaching a class last week, and it turns out one of my students was playing a game at the same time as trying to watch my lecture. So he had multiple monitors, and one monitor he was playing this game, and the lecture on monitor was my lecture. So that split attention also reduces increases cognitive load and makes you more tired. And then there's social factors. Interestingly enough, when you're on Zoom all the time, you know, you've got a camera on your face, you can see yourself on the monitor, and you're very aware of being watched, and you know, of people constantly staring at you. So that can be very draining as well. One of my friends, Dan Novi, tried to make Zoom more interesting, and so this is Dan. So he used Snapchat's AR lenses to be able to create Zoom events with him in different characters and different costumes, like Doctor Strange or Max and Where the Wild Things Are. And he said that it was great, except it kind of backfired, because he says now that people invite him to meetings just to see what he's going to look like when he turns up in the meetings. So that's kind of a funny scenario. So of course, Zoom isn't the only way to teleconference today. Many other devices, you know, on our mobile devices, sometimes people build these big teleconferencing suites, or you've got like things like iBeam where you can roll yourself around on a telerobot. But all of these things are quite different from face-to-face communication. Of course, face-to-face, you know, you can see some group of people here gathered around a table, and they're doing some sort of planning. And you can see in this case, you've got this ton of task space where people are focused on, and then the task space is really a subset of the overall communication space. And in the communication space, you can share a lot of cues, you know, non-verbal cues with gaze and gesture, speech cues, of course, and also, more interestingly, interacting with objects in the real space, like in this case, they're looking at this model or the building. So one of the challenges when you introduce technology into the mix is that you kind of have this separation between you know, the task space and the communication space. So in this picture, you've got, like I said, looks like they're models, but anyway, they're all looking at this computer monitor. So the computer monitor is the task space, and the communication space is really here. And it's actually quite hard to, it's quite hard to view the communication space and each other at the same time as you're looking at the screen in the task space. And the same thing happens on video conferencing suites as well. So here's a video conferencing setup. They've got two monitors going on, where on one monitor they're showing some sort of 3D molecule. On the other monitor, there's people's faces. So again, you know, task space is here and the communication space is here, and you've got this kind of seam between them. So there's a number of problems with current technology, and there's a lack of spatial cues, which means that people kind of blend into the background, poor communication cues with limited gaze and gesture, and also this artificial seam between the physical and digital world, and also the separation between the task and communication space. So people have been trying to explore how to overcome this. One of my students, for example, built a little plugin for Zoom that allows you to use the VR as a camera feed for Zoom. In fact, there's a company called Spaces that did the same thing, and they just got bought by Apple a month ago. So with my students plugin, somebody in VR can be talking or giving a presentation, and at the same time, they can stream that into Zoom as a camera feed. And so now you get more of a 3D effect. So this is a video of this working. So you can see kind of a standard Zoom call. But in the top left-hand corner, my student Prasant is there as an avatar, and he's able to take people through a space and pick up and move objects and navigate around. Also, he texture maps his desktop onto a image there, and so he can drag his desktop around with them as well. So it kind of brings some 3D cues back into VR, and you can do things like, in this case, he's drawing on a whiteboard with his character, and he can communicate in that way. And there's kind of a long history of trying to bring back the bodies into teleconferencing, and this is some of the work that I was involved with a long time ago. So on the left-hand side, there's an early augmented reality conferencing application we did where you could have video textures of remote people appearing in the real world. So this took video conferencing from the desktop into your real space, and it increased the kind of social presence or feeling you're really interacting there. And on the right-hand side is the Green Space project from 25 years ago, and this was a project where they developed a shared virtual environment between Seattle and Japan. And when you put the VR headset on, you go into a shared space, and again you'd see some colleagues in Japan there. It was the first trans-Pacific virtual environment, very basic of course for today. And then of course today we've got much more enhanced things. This is Outspace VR. About 2 months ago I had a chat with Tom Finesse, my old PhD advisor, and we all went into Outspace, and then you saw each other as immersive space as these virtual characters. And most recently, the last few months, Facebook has been beta testing the Facebook Horizon platform that will be a large-scale multi-user social VR experience where you can go into, use the Oculus Quest, and you can go into this 3D space and alter things together, and you've got these very cute-looking characters. One of the best examples of using mixed reality for communication is the spatial, and this is the spatial promo video. And in this video, what you can see is people being able to take pictures of themselves and then use those pictures to create an avatar, and then using the spatial platform, that avatar can appear in the real world as an augmented reality character. And then you can also drag other assets in as well. So in this case, you're seeing her now dragging in a bunch of pictures, or it was this guy here, he's having a meeting and he's opening up a workspace, and then pictures appear on the walls and the avatar starts appearing, and you can collaborate in your real world. And so this very naturally gets rid of that previous artificial seam between the digital task space and the communication space. You can share 3D models, look at pictures and post-it notes. Spatial also works on a variety of platforms, so with VR headsets or tablets or phones or desktops, so everybody can collaborate together. So it's a very, very nice collaboration platform. So as I just showed, with things like spatial, you can use the mixed reality or augmented reality to break that communication seam, because you can support very natural gesture and gaze cues and very natural conversation, and now the task space again becomes a subset of the communication space. So with many video conferencing platforms, the goal is sometimes to create the feeling of being there. One person said the total effect of this, this is the Cisco telepresence system, the total effect is to produce an environment at each end which is as close to possible as being there as possible. However, actually what you want to do is go beyond being there, and there's this really fantastic paper that was written almost 30 years ago now from Jim Holland and Scott Stornetta that talks about how that with telecommunication, we shouldn't focus on the tele part, but the communication part, enable ourselves to build tools that go beyond being there and develop tools that people want to use even if they are face-to-face, and things that you can't have in a face-to-face setting. So for example, tools that automatically record your communication and index it so you can go back a month later and recall what was said in a meeting, or tools that automatically support, like the augmented reality I showed before, the visualization of 3D content that you couldn't normally pull up in a face-to-face setting. So the goal really for next generation collaboration tools is to see how you can go beyond being there and do what you can do much better than in a face-to-face communication setting. So I'm going to talk a little bit today about how you can use AR and VR to go beyond being there, and doing things like changing your perspective or copying spaces or changing your body scale or sharing views and a wide range of other activities. So first of all, changing perspective. Actually, this is a very old picture, and this is the Cabinet project from British Telecom in 1992. And in this case, they put a camera on somebody's head with a small AR display, and they were able to live stream the camera view to a remote person that could basically see what you're seeing and then talk you through performing a task in the real world. And so they changed the perspective from being on the person's face to being on the task space. And they found that by doing this, it could produce a significant performance improvement. So Carnegie Mellon, a few years later, discovered that it could cut the performance time in half on certain physical tasks. And this is kind of our modern day version of this. This is one of my students wearing an AR display with a depth sensing camera on his head. And then the remote person can draw on the video coming from the head mount and send the drawing back. So in the head mount display, you can see this kind of AR annotation appearing in the real world. So you can easily guide somebody through a physical task. And so this has been researched for quite a number of years, and there are a number of companies that are producing products in this space. For example, Microsoft with the Remote Assist. But one of the challenges with this is that you don't know exactly where the person who is wearing the display is looking. You kind of have this trade-off where you want people to wear a very wide field of view camera so they can see as much of the real world as possible. But as the field of view of the camera increases, then you don't know exactly where the person's looking at objects in that field of view. So a couple of years ago, we developed this project called Empathy Glasses. And in this case, we combined together eye tracking with an AR display, and also with a special frame called the Effective Wear frame that could capture your face expression. And the overall goal was to provide the implicit communication cues that we oftentimes have in face-to-face communication, like gaze and face expression. So this is the setup here. You can see on the left, the person's wearing all this gear. They're also wearing a heart rate sensor because we want to measure their stress level. And on the right-hand side, this is what they see in the head mount display, and also the remote person sees. And the most important thing here, you can see my mouse, is this green dot. The green dot is the feedback given by the remote expert. So it's saying, okay, you should move this thing. And then secondly, this red dot. And the red dot is the eye gaze of the person wearing the display. So now what the remote expert can see is what the person who's wearing the display, where they're looking at exactly. And that's important because that provides a very implicit communication cue. So for example, if I say to the person, oh, you should move that object over there, I can tell if they're paying attention because their eye gaze will follow my pointer. So here's a video of the system working. You can see the person's wearing all the gear on the head. And now what they're doing is basically a block assembly task where they've got some wooden blocks and they have to build a little picture. And the remote person is using the mouse pointer to tell them where to place objects, and then they're watching their eye gaze as well. And we're also looking at their face expression and heart rate. And so you can see that the remote person can kind of tell if the worker is paying attention because the eye gaze spot will follow the pointer spot. And this will be really important. This is a pretty simple task, but you could imagine a task, for example, like bomb disposal, where you want to know whether the person's looking at the wrong wire or about to cut the wrong wire. And so you can tell it by their eye gaze. This is how the face expression system worked. We had some photoreflective sensors, and as you made a face expression, the distance to your skin would change, and we could detect that and recognize that you're making face expressions. So that was a really great project. And when we did some user testing, we found that sharing the eye gaze significantly increased the sense of social connection between the two people, as well as sharing that remote pointer. In fact, the remote pointer, some people said it felt like the person was kind of reaching out into their real world and showing them and had a presence in the real world. But one of the problems with that system is that it only shows a video view from the camera that's facing forward. And so the remote person doesn't really get a strong sense of situation awareness or immersion from the person's space. So more recently, we've done a project called the Shared Sphere, where you can live stream a 360 video. So there's a person wearing a camera on their head, 360 camera, and we can live stream that to a remote person who's inside VR. And so now the remote person can see the 360 video, can look around from any perspective, and can see the worker's surroundings. The remote person in VR also has a gesture sensor on the head mount display, so we can capture the gestures and send them back to the person in augmented reality. So you can see on the bottom there, the person who's wearing the augmented reality glasses kind of sees these ghost hands floating in space, in front of them and that can point at objects and show them what to do in the real world. And then, of course, because we've got both users that potentially could be looking in very different directions, we have to provide some clues about where everybody's looking. So we have a green square down the bottom and a red square, and these both show the other person where their partner's looking. So this is a video of the system working. This is a person in a power station, and they're trying to figure out how to fix this problem. They've got the Microsoft HoloLens on and now 360 camera. They can live stream the view to the remote person. And in the head mount display, this is what they see. So they can see these ghost hands appearing, and the ghost hands can draw on the real world or point at real objects, and they can communicate with audio, of course. So it makes it very easy to collaborate. And then that green square there is showing exactly where the remote person is looking. So they're both looking in the same direction right now. And this is a remote person. So we live stream the 360 video, and this person is immersed inside that video. And so to a certain extent, that person feels like they're really at the same location as the person sending the video. And as before, they can draw on the video and make annotations and so forth. One of the problems with this, though, is that we're only sending video. So the person inside the VR can certainly look around and feel like they're in the space, but they can't move through the space because it's only a 2D, it's only video on the system. The other problem is that it's quite expensive, and so most recently, just a few months ago, we've been developing a consumer version of the Sphere, something that everybody can use. And so it kind of looks like this. On the left-hand side, we have a person who's the host or the guide, and they have a 360 camera with a tablet or a phone on a selfie stick, and they can live stream that to a remote person who's on their desktop computer through the web. And then the person on the desktop can use their mouse to look around and can see the live stream again, and can also communicate back. So this is the kind of setup. We've just finished the initial version of this working. We're basing this on the Jitsi platform that you may not be familiar with, but Jitsi is an open source video conferencing platform that runs across the web, kind of like Zoom, but open source. And we've built our own 360 camera plug into that. And we've also added support for loading pre-recorded content. So you can load pre-recorded video or 360 still images. So this is the system working. We've got this lady going to the museum, and when she gets inside the museum, she breaks out the camera and the phone, and she can walk around through the space, and then she can live stream 360 from inside the space while talking to the people remotely. And then this is the remote connection. We've got a couple of people connected now, and the person opens up the 360 video, and then on their computer they can browse around and look around the video. And as I said before, we can also load up pre-recorded content. So now we're loading up pre-recorded content from inside one of the galleries, and even pre-recorded 360 images. One of the reasons why I'd want to do that is because the live video actually is fairly low resolution. So if you load up a pre-recorded 360 image, it becomes much higher resolution. And with the video, you can show things. For example, we just walked through that Maori collections hall. You might want to show, for example, a performance of some Maori performers in the space. And so we could have a video of that and play the video so we get an idea of what that is. So this is essentially a much more inexpensive and accessible version of the shared sphere. You don't need any special technology on the receiver side. It all runs through the web. It means that you don't even have to download a plugin or anything. You just go to the URL and you can see it. So we're in the process now of testing this to see what people's response of how this could be used today. But as I say, one of the problems with these types of systems is that you can't really go through the 3D space. So we're also working on 3D live capture. And so this is how we can do that with using a cluster of 3D depth sensing cameras. So we've got a cluster of 6 cameras here. Each of them captures a point cloud in front of them, and then we can live stitch the point clouds together and create a real-time live 3D model of the real world, which you can see on the right. So here's the video of that working. The left-hand side is a God's eye perspective. The right-hand side is a first-person perspective inside VR. This is one of our lab workspaces. And you'll see in a second a person walking to the space on the left. Here they come now. And as you can see, we can live capture that person as they're moving through the space. You'll see some obvious limitations though. With the blue, you can see there is where the cameras can't see. So we've got some occlusional or distance problems. And also the table in front is supposed to be a nice flat table. but there's actually a kind of a wave going through it because of the miscalibration of the cameras. But you get the idea. You know, with this technology, you could imagine in a few years, you might have some sort of handheld device where you could walk into a space and immediately start streaming 3D content from that space, as compared to 360 video. And we can also, so ways you could use this, for example, is you could set up this scanner inside a real space and then live scan the real space, or you can use it for remote collaboration. So you live scan to a remote side, and then the remote user points at objects or moves virtual copies of objects around and sends that back to you. So here's a video of this working. You can see on the left-hand side an augmented reality view of the real world, on the right-hand side a live 3D copy of that. And the person in the augmented reality is telling the person in the real world how to move objects around, so how to move that yellow object, for example. And you can see when they place the yellow object, it appears again on the right-hand side. So we can use this type of technology for a live remote collaboration on physical tasks. The setup on this case is a little bit different from what I showed before, in that now in this case we've got 4 cameras around the table, so it's capturing it in, so it's an outside-in capture system rather than inside-out. So you can see over the last few years we've gone from 2D sharing from a person's viewpoint to 360 video, and now to 3D live sharing. And this of course produces increased immersion, better scene understanding, and also better collaboration. But there's other things you can do as well. And so once you're able to copy the real world, and you know, as I've shown with the previous videos, you can have a situation where the person is in the real world and a remote person appears beside them as some sort of digital virtual avatar. Then you can add other communication cues that might help you. So for example, in this case, if you look at picture C, well, picture B is a condition where you've got 2 people in VR together. And just like in the real world, when you're in VR together, you can't tell the other person's looking unless you can see their face. But in picture C, what we've done is we've added a view frustrum or a view cone to each person's head. So now, even if I can't see the person's body, I have an idea of where they're looking because I can see this cone or the pyramid coming out of their face. So we did a project looking at how that we can use those for communication cues. So here you can see an augmented reality view of a remote collaborator. This, that view frustrum coming out of their face, and this is the virtual reality view of a remote collaborator. So now the people can work together in space, and they can use these communication cues to help collaborate better. So we did a user study to see whether or not having this view frustrum helped with the collaboration or not. And so in this case, we had to do a task where we were searching for boxes, and you can see now I can see the person's face and what they're looking at. But in general, I couldn't see the person's face, but I could tell where they're looking, so I could see these pink view frustrums going around in space. Of course, once you're collaborating between an AR and a VR situation, you can do other things as well. So one of the things you can do in VR is you can change your body scale. You can make yourself very big or very small. And this might be useful, for example, where you are trying to collaborate with lots of people. You can imagine maybe a firefighting scenario where you had a bunch of firefighters that go into a building. You're able to somehow scan the building, and you've got on the command chief back at the command center is able to use VR to look down and see a model or see the model of the building, but can make themselves very big, so they kind of get a god's eye perspective of these little miniature people running around in the real world. So here's a video of how that might be working. You can see on the right hand side a person in augmented reality, and the left hand side somebody in virtual reality sharing the same virtual space. And now what the person in virtual reality has just done is scaled themselves up 10 times or 4 times as big, sorry. So you can see the person in AR is a little pink head there. It looks like a very miniature person, and now they can move objects on a very large scale or create very big objects. And then in a minute, they'll scale themselves down to 1-to-1 size, and then they'll also shrink themselves down to smaller than that. So now they're back at 1-to-1 size, and they can manipulate objects together, and then they can make themselves really small. And so now they're a 10th normal size, and they can manipulate objects on the small scale, and they can see their collaborator as this kind of big head pointing at them. And of course, with this type of technology, you could also, the person in VR could jump into the view of the person in AR, and they could share the same view basically. So because you've got this AR VR collaboration, you you can collaborate many different ways. One of the other interesting things we've done is looking at how you can separate out the communication cue from body representation. So you can see in this picture here, you've got on the left-hand side 2 people collaborating together, but on the right-hand side, one of the people is behind the other person, so they can't see their face anymore, or what they're pointing at, and they're trying to look at this box together. So it's quite a common scenario in avatar experience or immersive VR, shared social immersive VR, where you again can't see where the people are pointing or looking because you can't see their face or their body. So we had this idea that you could create a mini-me avatar. So basically, when you can't see the remote person, this little miniature copy will appear of them in your point of view, and they'll always point to the same place that the actual person is pointing to. So they can share some of those communication cues you can't see anymore, like gesture and gaze or pointing. And this could be particularly important in the case of augmented reality, because many augmented reality headsets have quite a narrow field of view. So even if you could see the whole person, when you look away to look at different parts of the AR scene, you lose track of them again. So here's a video of the system working. So this shows, first of all, the problem with augmented reality with limited fields of view. You know, I can look at the person, but when I look at what they're pointing at, I can't see them anymore. So that doesn't help very much. So we've created this little miniature guy that appears remote from the person and points at the same place as that real person. So you can see now the miniature person standing on the box and pointing at that box, and the life-size person is pointing at the same object. So you get those communication cues if you can't see the person, the real person in the life size. And the mini-me appears when you move away from the person. So there's the person life size looking at them. And when I look turn my head away, this little miniature character appears, which stays in my field of view and is pointing at the same location. So this could be a quite common scenario where you're doing AR conferencing and the person appears in front of you as a life-size character, like in the spatial. But when I turn away from their body, I still want to see what they're pointing at. And so I now see a little miniature version of that person appearing around you. And then, oops, if I go back again, sorry, and just before I play this video, then we started playing with how you could, once you've got a representation of the remote person, how you could use that to change their viewpoint. And one way you could do that is you could attach a little virtual avatar of the remote person to a physical object, and then you can move the physical object around to drag their viewpoint around in the real world. So we call this on the shoulder of the giants, because the idea was that you could have a little person that rides on your shoulder, and then, if you know, you can see on the picture there, and that's attached to this physical object. We can pull the object off our shoulder and start looking and point at different locations in the real world to guide the person around. So if I go back and just start playing the video here. So what you'll see in the video, first of all, is this, if I just pause that for a second. So, and here you're seeing 2 views. On the top left-hand corner, you're seeing the external view of the person inside VR who's trying to fix the computer. On the bottom right-hand corner, you can see the view of the person, the top left is the person in AR who's looking at a real computer trying to fix it. The bottom right-hand corner is the person's view in VR, who's the miniature avatar. And what's going to happen is the person in the real world trying to fix the computer will move the avatar around by moving the physical object and point at different parts of the computer and to show them what they want to do. And then the person inside VR can, in the 360 video, can point with their controller at those locations and help the person perform this task. So let's play the video. So you can see on the right hand here, there's a little miniature avatar, and as she moves it around, you can see the bottom right view is showing different parts of the computer. And then she can put the avatar down on the desk and start fixing the computer. And the person is able to use their VR controller to guide them through fixing, in this case, installing a graphics card. And if you've got good eyes, you can see the little avatar gray guy there. He has a view frustum from his face again, and on the front of the view frustum is a video showing what he can actually see right now. We have a video texture showing what he can see right now. They're doing a high five together. So we did some studies to see how you want to represent the person. Do you want to show them as an avatar, or as a view frustum by itself, or as a combination of the view frustum and avatar together? And we basically found that the view frustum and avatar provide the best visual cues. So there's a lot of exciting things you can do with avatars and VR and AR to go beyond being there. One of the other things, which I'll go back to some very old work I did now, is that it's also very exciting to be able to use mixed reality to transition between the real and virtual world. So many collaborative experiences like the ones I've shown you exist either only in VR or only in AR. So for example, the Facebook Horizon, for example, is a purely social VR experience. The videos I just showed you had one user that was just in VR, one user just in AR. But you may actually want to be able to have technologies that lets you move between this continuum. So for example, you could imagine a person reading a book in the real world and then using augmented reality to enhance the pages of the book and having AR content popping out of the pages of the book, and then being able to immerse themselves in the AR content and go into a VR scene. And so, and you can do this in a collaborative setting. So let me show you a video of this work. And this is very old work that we did around 2000. So first of all, you'll see myself and another guy called Bruce, and we're reading this book. So here's two of us. And the great thing about books, of course, is it's very easy to collaborate with them because they're a physical object you can both look at the same time. So there we are reading this, the book. And what we can do now is we can take these AI headsets and pick them up and look at the pages of the book and see some augmented reality content popping out of the page of the book. So you'll see us pick up the headsets and now look through these handheld displays, and there's now some AR content on the page. And you'll see in a second what can be seen inside the page. So I think it's going to transition. Okay, so now, so on the page of the book, in this case, we see this little Japanese princess. But every second page is a space that you can fly into if you want to. So there's a little space. And if we want to, we just push a button on the handheld display and we can then fly into that space and experience it immersively. So we can now use the physical book to transition between AR and VR. So here's in this case, her friend Samurai's farm. And we can push the button and now we fly into the VR space and we can now navigate through the VR space. So of course, very crude graphics. This was 20 years ago, but you can imagine this being done today, much higher spec graphics. Now, once I'm in the farm scene, then my friend who's still in the real world should be able to see me in that scene. And of course, he's still seeing the AR content. So he should be able to see me as a little character in the AR view. And that's in fact exactly what happens. So you can see now from my friend's perspective, there's me in the VR space, and I'm just this kind of pink head that's going around. And so he gets a God's eye perspective on the collaborative space. And then of course, to keep the metaphor consistent, then when the person inside VR looks up into the sky, they should see a giant person looking down at them in VR, and that's indeed what happens. So you'll see that in just a second. So I think here we go. So now I can look up into the sky and I can see my friend as this giant avatar looking down at me. So there they are. Of course, we didn't have much budget or time in those days, so the people look very crude, but if we did it again today, we could easily texture map video onto that and make it look like a real person looking at us. And then of course what we can do is both people can come together in the same VR space and collaboratively explore the space together. So there's my friend with me as well. So as I said, this is very, very old work, but even today we don't really have commercial systems that allow us to seamlessly transition between the real objects through AR and VR together. We're kind of locked into either going into a VR space to collaborate or an AR space to collaborate. So I think there's a lot of potential in this. So in the Magic Book project I showed you today, you can see this collaboration on multiple levels. You can collaborate with the object as a physical object. face-to-face. You can collaborate as an AR object. You can also go into an immersive space, and you can also have, you know, egocentric or exocentric collaboration, and you've got individual views. So that means that, you know, in your own AR or VR headset, you can have some privacy. You can have different roles or different interfaces depending on who the person is. So again, that's really old work, but it would be fantastic to see that being redone again today. So I want to talk, we're almost at the end of the talk now. I want to talk a bit more now about future trends. And so in my opinion, there's kind of three important trends that are happening in the collaboration space. One is more towards experience capture. So we're moving away from just sharing faces and seeing people on Zoom to technology that allows us to capture and share places. So for example, the person on the right hand side here has put a GoPro camera on their head, and when they go skiing they can live stream that view to somebody else, or they can capture the experience. And I've already shown you some of that with the 360 video, so it's really easy, relatively easy now to capture a 360 video of your space. A second trend, of course, is much faster networks. So when I was first starting computing, I think I had a 56K modem or something very, very slow like that. And now in my apartment here in Auckland, we have a gigabit fiber connection. So we can live stream very high bandwidth video or lots of data to other people. So this supports more natural collaboration. Of course, you can have a full frame color video streaming, but also you have things like spatial, where you can stream high resolution 3D avatars or 3D content. And then the third trend is towards implicit understanding. And so what this means is that you can build systems that now recognize behavior and emotion. So for example, you can push the button on your phone and you can talk to Siri, and Siri understands your voice. You've got cameras looking at you now that can understand your you know, if you're running or standing or jumping. You've got cameras that look at your face to understand how old you are or what emotion you've got. So this allows us to build systems that can implicitly understand our state without us having to tell them how we're feeling or what we're doing. So these three things kind of overlap. So you've got, you know, natural collaboration, experience capture, and implicit understanding, and they really overlap in the space that we're calling empathic computing. So the idea of empathic computing is, can we develop systems that allow us to share what we're seeing, hearing, and feeling with others? And so of course, with today's video conferencing, it's relatively easy to share what we're seeing and hearing with other people, but the feeling side has really been largely unexplored. And so can we build systems that somehow capture people's emotions and share those with other people so they know more of what they're feeling? So in our lab, we've done some experiments in that space. This is one of the first ones we did, looking at sharing emotions inside VR. So we had a person inside VR and they were playing a game, and they wore the special biometric glove that was able to capture their heart rate and other physiological sensors. And then we could stream that to a second person, and the second person was an observer. So we put them inside the first person's virtual body, so they could see the VR environment from the same perspective. But they weren't playing the game, they're observing, but they could get some idea of how the person was feeling. And so we tried this out with several test environments. One was this kind of butterfly catching space where you could, in VR, you could try and catch butterflies in a very placid and nice, calming environment. And the second was a zombie killing game where you're in a dark warehouse and zombies are attacking you, and it was very, very scary. So of course your heart rate would go up. So here's a video of it working.
Sharing physiological states of players in collaborative virtual reality gameplay. Our goal is to improve and enhance users' empathy among collaborators, especially in a remote setting using advanced computer interfaces. To support this study, we developed a collaborative VR framework which shares the player's position and heart rate to the observer in a virtual environment. The observers view the game from the player's position, but can rotate their head freely to look around. The player's heart rate is measured by a biometric glove. The measured heart rate is shared with the observer using both visual and audio cues. We developed two games based on this framework. The first game provides a calm and pleasing experience where the player catches butterflies while surrounded by nature. The second game presents a scary and stressful situation where the player tries to survive zombie attacks. We conducted a study to learn the effects of displaying the player's heart rate to the observer. From the insights gathered in this study, we present a set of guidelines for designing collaborative VR experiences.
So that's the end of the video. But basically, in that study, what we found was that when we shared the heart rate of one person to the other person's heart rate also got elevated, and they felt more excited as well. And in a subsequent study, we looked at different ways you could share that information. So turns out having a icon on the screen isn't really the best way to share heart rate, but having a good audio cue, and especially pulsing the handheld controller and giving haptic feedback, was very effective. And we were also able to artificially enhance the heart rate. So you could measure the heart rate from the person in the game. You could speed it up by up to 20% and then share that with a remote person whose heart rate also accelerated and got more excited without them knowing that the person's heart rate was being artificially enhanced. So one of the reasons why we did this was not to make VR gameplay more exciting or better, but we want to mock up what it would be like to do this in the real world. So you could imagine, for example, sometime in the future where you've got maybe an Olympic athlete who is barreling down the mountain on the mountain bike, and we're able to use 360 scene capture technology to stream the video to remote people, but also share their physiological cues. So I could be sitting at home on the couch with my VR headset, seeing 360 video from the mountain biker and feeling their heart rate and somehow getting that level of excitement of being in the mountain bike race. So here's some of the results we found. Actually, I should have talked about this before. You can see the blue bars is the positive effect that's felt by the second person with the heart rate being shared, and the green bars without the heart rate being shared. So, and then there's a negative effect on those two games as well. So first of all, one thing we found was that indeed the zombie game was more exciting than the butterfly experience, but also people who shared their heart rate, the second observer was able to feel a lot more positive effect when the person was sharing their heart rate than not sharing their heart rate. And we also observed more communication within the collaborators as well. So in general, you can see a bunch of technology trends now that makes this type of research easier. So there's trends towards more advanced displays and so wider field of view, high resolution, scene capture technology, natural gesture and eye tracking, natural gesture tracking and eye tracking, and then also very interestingly more advances towards emotion sensing and sharing. So you can see the picture at the bottom here is a VR headset with EEG sensors mounted in it, so you could potentially record the brain activity happening. And in fact, this has advanced quite a lot in recent years. So this is the Lucid Link EEG mask, and what you do with this is you plug it into your VR headset, your Vive headset, and you can measure the brain activity of across 6 electrodes on the forehead, and this integrates in with Unity, and you can live stream the raw EEG data into your app. Measuring the brain activity on the front of the brain is good for cognitive load, but it turns out the visual cortex is in the back of the head, so you may want to measure from there. And there's this company called NextMind that has built an EEG that will go into a head strap that can fit at the back of the head. And this is not very expensive, so this costs about $400, and I think the Lucid Link, we just bought another one that was $300 US, so it's relatively inexpensive. And in fact, just this week, Hewlett-Packard announced their new OmniSet head-mount display. So in November, Hewlett-Packard is releasing the HP Reverb G2, which is a Windows mixed reality VR headset, and it has a very high, very wide field of view and very high resolution. So it's one of the best in classes VR displays. It plugs into your PC. But with the OmniSept, which they're going to release in early 2021, they also add into this eye tracking, heart rate information, pupillometry, and a face camera. So they're capturing a lot of physiological information from the head-mount display. And you can use this a number of ways. So for example, you can use this now to map onto VR avatars, make avatars that behave a lot more realistic in manner. Or like I showed you before, you could use it to infer stress or emotion and share that as well. And in our lab, we haven't had that luxury of having these devices yet. So one of the systems we put together about 6 months ago, I guess, was to build our own version. So in this case, we had a faceplate, and inside the faceplate, we put EMG and EOG sensors, so we can measure the muscle motion on the face. And then we had people wear an EEG cap on their heads to measure the brain activity. and also some physiological sensors on their hands, like the shimmer that measures the heart rate or the GSR level. And by using systems like this, you can start measuring brain activity inside VR. So one of my students is using this, for example, to trying to build VR environments that respond to your contextual cues, use contextual cues to create emotion and respond to your emotion. One of the really exciting things I'm excited about, though, is using it to look at collaborative experiences. And it turns out that about 10 years ago, people discovered or started to explore more the phenomenon of brain synchronization. So it turns out if two people wear EEG brain caps and they start doing a similar physical task, so in this case, two people are pointing with their finger, and as you move the finger around, the follower's finger matches the leader's finger. It turns out when you do this task in the real world, then you can measure people's brain activity, and in some cases, the phase of the brain waves will come into sync. And when this synchronization happens, people report that they feel more in tune with the other person, or they're collaborating together better, or they perform better. So this is what it looks like when doing the task. This is the brain activity. So here's the two brains, and the black dots show the EEG electrodes. And then you have a kind of a heat map of activity happening. So there's nothing happening really right now, but as I said, you do this finger tracking task, and then you do that for about a minute, and then you stop the finger tracking, and then you rest. And while you're resting, sometimes your brain looks like this. And so you can see now these loops going from the left to the right head. And what those show is these show connections between the electrodes that have the same amount of phase synchronization. So it shows that some of the electrodes now, or some parts of the brain, are becoming into sync. So this has been studied before in a number of real world cases, but until now, nobody had done that inside VR. So earlier this year, actually late last year, we did a VR experiment. So here's two people inside VR. Of course, because they're in VR, they don't need to look at each other in the real world anymore. So they're both inside VR with the VR headsets. And when they inside the VR environment, they can see an avatar, and the avatar also does the finger tracking experiment. So you can see there, one person's moving their finger around, the person with the dark gray finger, and the person with the white finger is trying to follow that. And it turns out we made some measurements, and we could also observe this brain synchronization. But what's more interesting though in VR is you can take one person's perspective and put it inside somebody else's body. And so this is what that might look like. You look down, and now you can see two pairs of hands, and now in synchronization with each other. So now the goal is to basically, when the dark hand is moving, the light hand should try and follow it. And so when we did this, we also measured the brain activity. So you can see here, this is before we started that task. There's the two heads, and the red dots where the electrodes are. This map shows areas of synchronization. You wouldn't normally expect synchronization before we start the activity, but also one of the reasons why we've got so many lines is because we take each electrode and we look at matched up with each other electrode. So there are basically hundreds and hundreds of matches being performed, and so you'd expect from that a few false positives. So this is before we start the task, and then this is after the task. And now what you can see is some very strong red lines appearing, and this shows where you've got more than 3 or 4 areas of the brain starting to synchronize with each other. But this is just a very early experiment, and we're still actively researching this. The goal basically is to look at, can we use AR and VR cues to enhance the brain synchronization, and so enable people to feel like they're more connected to somebody else and collaborate better in the real world. But as I said, it's very early days yet. And you can also use it in interesting ways. So in this case, let me just pause the video, for example, and explain what's happening. In this case, we're using brain synchronization for a simple game. So now we have, you'll see here in the video, 2 people playing a kind of a drumming game. They've got some real objects on the table in front of them. They can hit the objects with these big drumsticks, and they're both wearing VR headsets. And as they start drumming, we measure the brain activity, and if the brain activity starts becoming in synchronization, then we change the VR view, and we make add a lot more visual effects to provide more visual feedback. We picked drumming because drumming, of course, is a very rhythmic activity, and so it's more likely to increase that brain synchronization. So let me play the video and turn the volume up, and you can hear it.
Neural Drum is a VR drumming experience that allows two players to drum together while their brain signals are simultaneously measured. At first, you can set some daily objects on a table to use as drums. A player will use two drumming sticks to play the game. Both of the players will wear an EEG capturing hardware to get their brain signals measured from the frontal lobe. The data acquired will be streamed to the data processing system to enhance VR experience, depending on the player's collaborative performance. We designed a software to calculate the phase locking value, which is an index of neural synchronicity, for the FP1 and FP2 channels of the theta band from both the participants. When synchronization between two players is low, the camera will be more clear to do so, whereas when synchronization is high, the vision becomes more obscured, with each point cloud eliciting higher particle effects. We logged and analyzed the user.
So I'll stop that. Let's go back, sorry. So as you can see in the video, when the brain synchronization starts happening, we have a view of the collaborator in the real world, but as the brain synchronization starts happening, we make that more transparent, and we bring up these particle effects and other virtual cues to help stimulate and encourage the game more. And then we showed this at SIGGRAPH Asia last year, and we did a study of participants who played it, and we found that people who were more synchronized with each other rated the playing experience much more excited, and they felt more connected to their partner as well. So where does this kind of trend towards? Well, you can imagine, as I've shown you, you've got these new technologies like advanced displays and motion sensing, and all these can kind of combine together to create this empathic teleexistence experience. So the basic idea is that collaborators should be able to move from being an observer, an external observer, to being a participant with their partner in a real experience. So you can transition from explicit to implicit communication. You don't need to tell the person what you're about to do, because they can see it and they can know how you're feeling. And you also have this idea, you have this experiential collaboration where you really are doing things together. So there's been some, this is sounding a bit like science fiction. In fact, these still images here are taken from the Black Mirror show. There have been some, I guess, hypotheses about how this might end up in science fiction. And one of them is this really bad movie that had Bruce Willis in it from 2009 called Surrogates. And the premise of the movie and Surrogates was that in the future, we'll all be able to inhabit robot bodies. And the robots will be able to send data back to us in our VR headset, so we can see what the robots are seeing, we can feel what they're feeling to some extent. And because the robots are robots, it means we can do things that we'd never do in the real world, like we can jump off buildings, or we can fight each other, or we can go run very fast or pick up very big objects, and then all without harm. But in the movie, the premise is that after a couple of decades of never having a real person being murdered or hurt, suddenly people start getting murdered, and Bruce Willis has to kind of solve this crime that's happening in the real world, and somehow affecting people in their VR spaces. So I'll play the trailer. You can see it is here. So here's Bruce Willis going into the VR system, and then you'll see surrogate Bruce Willis, and you can tell the difference because he's got hair in the surrogate one. So here's Bruce Willis as a robot surrogate, and of course everybody looks very beautiful. And then here's a guy jumping off a building, and he's perfectly happy. And now somehow he gets killed, but not only does the robot get killed, but also the person in the real world in VR somehow dies as well. So that's all very exciting. And so that's the future. Well, no, that's one vision of how we might have this kind of tele-existence in the future. And it may sound very like science fiction, but actually people are doing this for real for now. So here's an example of a robot in Japan that provides some type of tele-existence. So you can see on the left-hand picture there, you've got a person in this VR headset. And then right beside them is a robot that has cameras and microphones and hands, and the person in VR can drive the robot as if they're inside their body. And the professor that worked on this, Professor Tashi in Japan, actually started a company, and now you can buy these for real. And so here's the promo video for the company. So you can see the guy's going to go to a surf shop in Hawaii, and he puts on his VR headset, and then there's the surrogate robot, and the surrogate robot is in the surf shop in Hawaii. You can move through the space, and he can talk to the shop owner, and he's now touching the surfboard with the robot, and then remotely in his VR headset he can feel what the board looks like and presumably make a sale and buy the surfboard doing a selfie. And after he's bought the surfboard, then his son comes down, the son decides he wants to go with him, and they now go to a new location. They're going to go to Kyoto to look at the Cherry Blossom Festival, and now through the surrogate robots they feel like they're in Kyoto. So perhaps that's might be one way we might experience the future, or the world in the future. So these robots aren't cheap. I think the tele-existence sells them for about $100,000 each. But the idea isn't to buy a robot. The idea is that you'll have dozens of these robots scattered around the world, and then from your home VR system you can jump into a robot and rent it for a few minutes or an hour and have this tele-existence experience. So that's pretty much what I want to talk about today. We've talked about how current conferencing has a number of limitations, both physical and cognitive and social shortcomings. I've shown you different ways that AR and VR can enable going beyond being there. Things like changing your perspective, sharing your space, changing your body scale, supporting nonverbal communication. And then I've also talked a little bit about directions for future research, in particular, what we're doing in empathic computing and looking at brain synchronization. And then work that's being done now in tele-existence. There's also a lot of work that needs to be done on how to represent and share emotion. It's one thing to be able to record from somebody physiological signals that show that they're feeling stress or feeling happy or feeling sad, but then it's a whole different thing about how do we present that to somebody else and have them be able to empathize and share those feelings. So thank you for the time.